Hello everyone and welcome to another video. Today I want to talk briefly about Cartesian, polar, cylindrical, and spherical coordinates. And this is going to be a pretty quick discussion because hopefully this is somewhat familiar to you already. So all of these are basically different ways to describe a location in space. That's the whole idea with what a coordinate is, right? It's basically a way to tell someone else how to reach a certain location in some space. So the easiest way to start off with this, I think, is let's think about a one-dimensional example where there only is like a line. And actually, I've got a little prop here to help us. So here's my my red for x-axis, and maybe let's go ahead and see if we can sort of tape this on the board, and we'll just make this is our coordinate system where there's only one dimension to it right now, okay? So here we go. So you can only move along the positive x direction or the negative x direction. So to start off, Cartesian coordinate systems is really simple. It's basically saying, let's say I want to get to some point, like this point is out here, this black dot. Let's call this point P, how about? Okay? So a Cartesian coordinate system is basically, I need to tell someone, if you start here at the origin of this coordinate system, how do you get to this location? Well, you have to walk or move a certain distance. Let's call this distance here x, right? So this point, you could go ahead and if we want to describe this in Cartesian coordinates, right? You could just say, all right, this point P is located, you would give someone this number x, right? And that would basically imply that you walk along this direction for x units until you get there. Now, let's expand the space. Instead of saying just being one dimension in x, let's how about have an x and a y? So maybe let me add, I've got the red here for x, I've got this green here for y, so we'll draw it in this direction. And now this point P can be anywhere in the plane here, right, of x, y. So I tell you what, let's move it, I don't know, maybe up like there or something like that, okay? So in this case, you've got this point P located in space. And again, what you want to do with Cartesian coordinates is you want to tell someone how to get to this point by basically following these set of axes which happen to be at a right angle from one another, right? So in this case, what you're going to tell someone is, okay, you need to walk x units along the red axis, and then you need to walk y units along this green axis, right? So this same point P in Cartesian space might be now, instead of just one number, you have to give them two numbers, or like a vector if you want to think about this. It's basically a tuple of unit of length 2, right? This is a 2-element tuple or vector or list. However you want to think about it, you're basically giving somebody two numbers, right? And that describes how to get there. So it has the understanding that you have this coordinate system where you have a red axis or an x-axis and a green axis or a y-axis, which are 90 degrees from one another, right? And you give someone these two numbers, that tells them how to get to that location P, okay? Now, you can have a variation on this, right? Let me slightly redraw the picture here. Let me just draw the, here's this x distance here, okay? All right. What if you wanted to, instead of using this this square or this rectangular Cartesian system, what if you wanted to use what are called polar coordinates? Now, polar coordinates, it's the same idea. The coordinates is still trying to say, I'm still trying to get to this location, but I want to do it in a different fashion. So what I want to do now is, first, I am going to go ahead and I am going to angle or point towards the point P through some angle theta. So in other words, let me draw it like this. I'll maybe draw this dashed line like that, okay? And now the angle that this dashed green line makes with this red axis, let's call this theta, okay? And the distance here is now, let's call this distance r, for a radius, right? So another way you could describe this point P here is you could give someone two pieces of information, namely the radius and this angle theta, okay? So these two pieces of information still tell someone how to get this location P, but they're decoded in a slightly different fashion, right? You see now we have a little bit of ambiguity here, right? Because if you gave someone just two numbers, you have to tell, are those two numbers, do they mean in the Cartesian coordinate system or do they mean in the polar coordinate system? So to help with that ambiguity, maybe what we should do here is let's give this maybe, I'll give it a vector notation here because we said it's 2 elements long, but also let's give it a subscript, or sorry, a superscript notation C. So C here denotes Cartesian coordinates, and over here maybe let's give it a superscript P for polar coordinates, right? Now we see that given this picture, we see that there's a pretty easy relationship between the vector expressed or the point expressed in Cartesian coordinates and the point expressed in polar coordinates, right? So to get that, that's pretty simple, right? We can basically see from geometry to go from polar to Cartesian, right? What we will have is, well, that's pretty easy. X we see, it's just what? It's R, because I guess there's, you can see there's a right triangle here, right? With a hypotenuse R. So R cosine theta is going to give you X, and then R sine theta is going to give you Y, right? So we have X is basically R cosine theta, and Y is R sine theta, right? So another way that we could write this is we could say that the point in the Cartesian coordinate frame, right, it's some function of the point expressed in the polar frame, and here's this function f here. So in this case, f is basically, it's r cosine theta, r sine theta, right? So if you give this function f a coordinate in the polar system, this is going to return a point in the Cartesian system here, right? So it's a very simple mapping, okay? Now, let's think about the inverse mapping, right? What if you had a point in the Cartesian and you wanted to go to polar here? So the inverse mapping, right? So the inverse mapping is, well, again, from geometry, we could either solve those two equations simultaneously for r and theta, because what we're looking for at this point is we want to say r and theta are equal to something here, where the something is a function of the Cartesian coordinates. Well, the radius is pretty easy to see, right? You can easily see that the radius is what? It's square root of x squared plus y squared, right? And theta here, you've got to be a little careful here. It might be very tempting to say, oh, theta, this is pretty easy. This is just the inverse tangent of y over x, right? But if you remember our discussion, we had a previous video where we talked about the 4-quadrant inverse tangent, right? This is a little bit scary because a normal inverse tangent is only going to give you 2 quadrants. It's only, the inverse tangent is, well, tangent is not a real function, right? So the inverse tangent has to pick a certain range. So this only returns values between, usually between positive pi and minus pi, right? So the issue here is we can't just use a normal inverse tangent. In order to make sure this is correct, you actually have to use a 4-quadrant inverse tangent, or a tan 2, right, of y comma x, right? Okay, so this is basically your inverse mapping. So now if you wanted to get a coordinate in the this point P expressed in the polar system, this is now f inverse of the point in the Cartesian place, where f inverse is basically, here's the mapping, right? Okay, so that's the concept of Cartesian and polar coordinates. So I think we can say check, check. Let's quickly talk about cylindrical. And cylindrical is actually really simple. It's the extension of polar and Cartesian to now to 3 dimensions. So in this case, let's go ahead and add a third dimension, right? So now instead of this point P being constrained to be in the board, let's add a third axis. So I've got red, green, how about now a blue axis? So we'll stick this onto our little prop here. Whoops, and now I guess I'm gonna need some more tape to hold this thing down. Okay, so here's our coordinate system in the board, and I know that's probably hard to see from the camera, but I think you get the picture now. So now this point P can be anywhere in space, and the distance, the projection from this space perpendicular to the board, let's call that distance Z along this axis. And now that you have this idea, maybe it would be better if we could maybe sketch a 3D picture of this on the board so we can start labeling some relevant geometry. So tell you what, give me a second to erase a part of the board and I'll redraw this. But all right, so like I said, I want to redraw this in a slightly reoriented fashion. Let me pull this tape off so I can show you the reorientation that I want. I basically want the Z-axis pointing up. So I want to take this and we are going to rotate it like this. So kind of like this, okay? So I'm going to draw this in the board with X kind of coming out, Y going also kind of on the floor, and Z kind of pointing up, okay? So let's do that. So let me go ahead and erase this picture here, okay? And let's redraw the coordinate system that we want, okay? So what I'm going to do is, let's draw this with the x-axis like that, the y-axis like this, and then the z-axis pointing up. Okay, so again, let's just double check. That should be a right-handed coordinate system, right? So x, y, and z, right? Yeah, okay, everyone remembers the right-handed rule, right? X is your index finger, right? Y is these middle ones, and z is in the direction of your thumb, right? I like to joke, this is kind of this is like, I think about this as the engineering gang sign, right? If you flash this at a couple of other engine nerds, right, and they know what you're talking about, you know that you're all in the same gang, right? So the right-handed rule is the engineering gang sign. So anyway, here's our XY. And now we said that this point P is now in three-dimensional space. So here's this point P. Okay, so you could either describe this in Cartesian coordinates and say this is an x, y, and a z distance, right? So it would mean you walk x units along the x-axis, y units along the y-axis, and then z units along the z-axis to get to this point. Now, the picture we had earlier with polar coordinates is that the angle theta was the angle that there was between the x-axis. So let's project this point down to the xy plane. So I'm going to go draw it like this maybe. Okay. Okay. And now what we've got is an angle or a line from the x-axis, and we're going to now sweep in the xy plane until we hit this point. Okay. And this distance, or this angle here, this is going to be that same theta we were talking about earlier. This is sometimes referred to, give this a name, an azimuth angle. This is sometimes referred to as your azimuth angle, right? And then you can see that the point from here to here, that's that distance r we were talking about earlier. So this distance in the xy plane, right? This is r, right? Or the kind of radius, right? And I'm going to put this in quotes because you can see it's the projected distance of the point in the xy plane. And then the distance from here to here is z, right? Just from the xy plane up to the point, this is the distance z, okay? So we see that really cylindrical coordinates is basically just polar coordinates with a z-axis, okay? So let's write that down. So in vector notation, that again, the point P in the Cartesian system, it's just x, y, z, right? That we talked about earlier. And now what we see is that the point in this exact same point P, but now in cylindrical, so C is going to stand for cylindrical coordinates, right? This is now going to be r, theta, and z, right? So these three numbers basically in either coordinate system will tell you how to get there. They just mean slightly different things. You move in slightly different directions depending on what coordinate system you're specifying. So again, we see that the x and y are theta. Those are the same. This is the same mapping between Cartesian and polar that we were talking about earlier. And z doesn't do anything. Z is the same in both, right? The z direction is the same in the Cartesian, and it's the same in the cylindrical coordinates. So again, if we want to be completely formal about this and write down the transformation or the mappings from one coordinate frame to the other, we could say that, you know, the Cartesian coordinate system, it's if you want to get there by given a oh gosh, sorry. I just realized, no, this is bad notation. We shouldn't say C and C here. We got to come up with another notation, right? Because C was for Cartesian. We need another notation for cylindrical. I accidentally, you know what? We can still use, let's use P here again, because polar, we see that polar and cylindrical coordinates are basically the exact same thing here, right? And you'll see that when we write down this mapping, right? Because we said that this is now going to be what? R cosine theta, R sine theta, and Z. Z doesn't change. So again, this was the exact same mapping that we had earlier. So the inverse is just the same, right? So this point in the polar or cylindrical coordinate systems is the inverse mapping. So you pass it now, if you want, you give it x, y, z, and I want to return r, theta, and z. So this is the exact same mapping we had earlier. So the radius r is just going to be x squared plus y squared. Theta we were going to be careful about. We were going to use a tan 2 of y and x. And then z is just z, right? So there we go. This is pretty simple. So let's take a look at an example just to make sure we're all on the same page. So let's look at an example. Okay. So what's my point? Okay, let's go ahead and pick this point P in the Cartesian coordinate system to be -3, -1, -4. Okay. So I guess if you wanted to draw it in here, so we were going to have to go -1 units in the x, -3 units in the x, right? -1 unit in the y, and then -4 units in the z, so down. So I know this is a little bit hard to see, but basically P is down here. So maybe it's easier if we look at our system right here. So here's x, y, and z. So really the point P is hanging out kind of down here, right? And this is kind of hard to see. But what we can now do is let's go ahead and use our mapping here to go ahead and compute what is the equivalent radius, azimuth angle, and z location. So if you just go ahead and run it through these equations, right? So in order to get, oh, sorry, I was pointing at the wrong one, down here, right? So what I want is I want this same point expressed in the cylindrical or polar coordinate systems. So I am looking for the r, theta, and z values. Okay. To get that, I'm just going to use my inverse mapping here. So this is just going to be square root of -3 squared plus -1 squared. And then it's going to be a tan 2 of y and x. So this is going to be -1, -3. And the z is just going to be z. So this is going to be -4. Okay? So if you go ahead and run those numbers, what you're going to end up with here is the radius is going to be something like 3.16. This here, now again, a tan 2, this is going to be, you really want to make sure you use a tan 2 because exactly this example, if you had just used a normal a tan, you would get the wrong answer. Theta would not come out to be the right answer. In this case, if you use a tan 2, you see that you do get the right answer. This is going to be -161.56-ish degrees. Again, be careful, right? This is then degrees instead of radians. I like to think about degrees just because it helps me visualize what's going on. And then z is just going to be -4. So no biggie, right? So great. This is basically the point in the cylindrical coordinates, right? So in order to get to this location of -3, -1, -4, you either use the Cartesian coordinates and walk -3 units in the x direction, -1 units in the y direction, or -4 units in the z direction. Or if you want to alternatively get to that exact same point using cylindrical coordinates, well, first you go ahead and turn 161 degrees in the negative direction, right? Then you walk in that direction for 3.16 units, right, along the radius, and then you move -4 units in the z direction, and that will get you in the exact same location. Now, to double check ourselves to make sure we're all on the same page, what we should do is let's go back and take these polar coordinates or these cylindrical coordinates and verify that we get back the same Cartesian coordinates, right? So let's go ahead and check that we recover the same Cartesian coordinates. Okay, so in other words, what I want to compute here is I want to compute x, y, z, and maybe let's call these like primes, because these are going to be like our check values. And the way I'm going to compute these is I'm going to go ahead and use our forward transformation of, given the Cartesian, or excuse me, the cylindrical coordinates, compute this, right? So it's r, which is what? It's 3.16 times cosine of, I guess we're going to have to, minus 161.56, but I got to convert this to radians, right? So pi over 180, right? And then the y value should be r, which is 3.16, times sine of minus 161.56, again, times pi over 180 to convert to radians. And then the z should be -4. Okay, so again, if you go ahead and you walk over and you compute these numbers and you crunch all the numbers, yes, they all check out. Basically, you are going to get this to turn out to be -3, -1, and -4. So this does check out. So both the forward and the reverse transformation, in this case, we didn't lose anything. And in fact, in all situations, you won't lose anything. And I'm only harping on this because in a second, when we go to spherical coordinates, this becomes a little bit more non-intuitive. Okay, so I'll tell you what, this is a good spot to discuss, to leave it for cylindrical coordinates. So why don't we go ahead and move on to spherical? So give me a second to erase the board and we'll be right back. All right, so let's move on to spherical coordinates. So spherical coordinates are similar to cylindrical coordinates in the sense that, tell you what, let's take a look at my prop here again here of my Cartesian coordinate system. So again, red is x, green is y, and z is blue, okay? So let's say that you've got this Cartesian coordinate system and you've got a point that is, maybe in the all positive direction, right? It's where my finger's pointing. Like, let's pretend that this is the point that we're trying to reach, okay? So the azimuth angle theta that we talked about earlier, that's a very similar definition. Let's go ahead and take this piece of cardboard that I'm trying to use to represent a plane, and I'm going to align this plane to start with the x-axis. I don't know if you can see that here, right? With the red axis. Maybe let's stare down the z, okay? So what we're going to do right now is we're going to sweep this, rotate it until we get till the plane basically hits the point of interest P. Let's pretend it's right here. This is where it's hit. So this angle between the cardboard and the red axis, the x-axis, that is still my angle theta. So it's right here where my thumb is. I'm trying to get a good picture here with the camera, right? So this is that angle theta, right? That's that azimuth angle that we were talking about earlier. Now, the difference with spherical coordinates is to get to that point. Let's go ahead and I'm going to move this and get another view. Let's hold that plane at that azimuth angle theta, okay? I'm going to try to hold it like such. This is going to be a little bit hard. Let's pretend that the point is, let me draw it. Actually, I could probably draw it in pen now. This point is out here. Here is our point P, okay? So it's in this plane, right? So again, let me kind of, this is kind of hard to see with all of the pictures going on, right? But that's the point. So the way we're going to get to that point is actually, we are now going to, in this plane, okay, this cardboard piece of paper plane, this is really difficult to hold with one hand. Okay, what we're going to do is we are going to draw another line that comes from the z-axis, and we're going to sweep down from the z-axis until we get to this point P, okay? So this orange little pipe cleaner that I'm using is supposed to represent that distance, okay? Or this vector. So now what we have is this angle here between the z-axis to this line, okay? This is what we're going to refer to as our inclination angle. I'm going to label this as phi, like such, okay? Like that. And the distance from the origin to the point P, this is now going to be the radius r, okay? So this is the picture that goes along with that. I know this is probably a little bit difficult to see, so I just wanted to show you this prop in 3D because I think that'll help us draw this on the board. So hopefully if this didn't butcher it too much, hopefully it sets the tone, let's go ahead and redraw this on the board in maybe a little bit more clear fashion. So again, let's draw our Cartesian system first because again, that's the easiest thing to look at, right? So here's x, y, z. Okay, and again, the point P of interest is maybe out here, P at x, y, z, right? Okay, so we said that, again, what we're going to do is let's project this point P down to the xy plane, okay? So I'm going to go ahead and project this thing down to the plane, okay? And now we're going to sweep, here's the piece of cardboard, we're going to sweep a plane from the x-axis to this projection here. So this, whoops, yeah, that was pretty reasonable, right? Here was that azimuth angle theta here. So here's theta, which is, again, we called it our azimuth angle. So this was the same in the cylindrical and polar coordinate system definition, okay? But now what we want to draw is we're going to draw a line from the origin of the Cartesian system directly to point P. So this, you know, comes straight from the origin out to here, okay? And now the angle that this line makes with the z-axis, and again, this is going to be hard to draw, and this is why I wanted to show it on the board or with the cardboard. This is our angle theta, or phi, excuse me, which is our inclination, or sometimes referred to as or polar angle. Okay, so again, keep in mind that this angle is from the z-axis to this point P, okay? Or sorry, to the line that joins that, right? Okay, and finally, the distance from the origin to the point P, this Euclidean distance here, this is the radius r, okay? So a couple of things that we want to note before going any further, okay? So note, hopefully this has given us enough context that you can see what's going on, but note that r in spherical is different, right? It's not equal to the r in cylindrical / polar coordinates, right? The radius, this r term is different. In spherical coordinates, it literally is the radius from the origin to the point. In cylindrical coordinates, right, it was the distance from the origin to the projection in the plane. So it was this distance here. So sometimes you might see in spherical coordinates, this might be referred to like as rho to differentiate it from a radius in cylindrical coordinates, but we're going to see that actually the nomenclature gets messed up quite a bit. What I mean by that is, to further complicate matters, in a lot of cases, the definition of theta and phi are switched. So in some fields, like physics, right? A lot of times if you read notation, you're going to see theta is the inclination angle, and phi is the polar angle. Or sorry, excuse me, or the phi is the azimuth angle. See, I'm getting it messed up. To further complicate, sometimes they'll actually throw rho in for one of these angles just to try to make everything consistent. So long story short, you got to be a little bit careful. Sometimes these definitions are switched, sometimes rho is thrown in there, what have you. Just be careful. We are going to adopt the notation here that a coordinate in spherical coordinates, so let's say this point P in spherical coordinates, let's call this a radial distance. Is going to be the first thing that you have to tell someone. The second thing you have to tell them is the azimuth angle. And then the third piece of information is the inclination / polar angle. Okay, and we are going to use the names of r, theta, and phi. Okay, so again, be careful. Sometimes what we're using is this, right, which is kind of the, I think a lot of times in mathematics, you'll see this nomenclature, but in some other fields, like I said, in physics, they're going to see maybe they use rho for that, and then they switch these definitions. So here's physics. So again, just be careful that you know what you're looking at. So again, we're not going to use this. Let's just focus on this discussion here, okay? All right, so once we've picked a set of nomenclature, I think it's pretty easy to go about doing the forward transformation. So in other words, just to refresh our memory, right, what we want is I want now a function to recover the Cartesian coordinates given the spherical coordinates, right? So let's first look at x, okay? So how do we get this x distance? And maybe I'm going to draw in a different color. Where did I put my other pen? Geez, oh, here they are, sorry. Let me hop off camera for a second, grab a pen, just so we can use this to draw these distances. So x here, we're going to have to take this projection. We're going to go in the plane here. So here's x, and then maybe I'll extend this a little bit so we can get the y component also. So let's project this so in the plane. Is that, yeah, that looks pretty good. Okay, so here's y, here's x, right? And then z is we're gonna again, oh shucks, I guess I ran out of room. Let me extend this picture a little bit just so we can kind of more accurately draw the projections. So now this point z has got to be projected along in the same direction here. So this, I'm going to try to draw this parallel. There, something like that. So that's z. Okay. All right. So actually, if you look at this long enough, z is probably the easiest one to get to first, because if you notice, right, this is a right triangle. Okay. And the hypotenuse of this right triangle is r, and this angle here is phi. So this distance, which is z, right? That's just r cosine phi, right? So z is just r cosine phi, right? Okay. All right. Let's look at another right triangle. Let's look at this triangle here, okay? And if you notice, right, this is a right angle, right? Okay. And this angle right here, isn't this actually, this angle is going to be what? It's 90 degrees minus phi, or I guess pi over 2 minus phi. Right? Wouldn't you agree that that's what this angle right here is? Right? And again, this has a distance r. So actually what we can get is we can get this foot, right? This foot is the distance of the projection in the xy plane, right? So that's just going to be what? It's going to be what? R cosine of pi over 2 minus phi. So again, let me draw it in bold, right? This leg, right? Maybe let's do this over here. I'm going to make a slight note. So let's come over here, right? This distance here is r cosine pi over 2 minus phi, like that, right? And if you remember your trig identity, this cosine of pi over 2 minus phi, this is the same thing as r sine phi, right? This time it turns into sine, right? So this distance here, this bold distance, is going to be, well, I guess it's just right there, right? So this is going to be r sine phi, right? And now, since we've got this distance, we can look here in the plane. Here's another right triangle right here. Okay? So you've got the hypotenuse here, you've got this, and then we know the azimuth angle theta is exactly in that plane here, right? So this distance x here is going to be hypotenuse times what? Cosine of theta, right? So that's going to give us x. So the x is going to be, what's the hypotenuse? The hypotenuse here we said was r sine phi times cosine of theta, right? There we go, right? That'll give us this distance x. Y is the same thing, right? Because it's just this distance here. So it's just hypotenuse times sine of phi. Of theta, right? Hypotenuse times sine of theta. So hypotenuse is r sine phi, right? So that's the hypotenuse times sine of theta. There we go. Okay, so here we go. This here gives us, the left-hand side, this is basically the coordinate in the Cartesian system. And here is the forward transformation, or the forward mapping, to get those Cartesian coordinates if you have them in the spherical coordinates here. So here's the mapping, right? So we've gone ahead and said, if someone gives you, if you know what the radial distance, the azimuth angle, and the inclination, the polar angle are, you can easily compute what x, y, and z are, right? Now, maybe we should have mentioned this earlier when we were also discussing the cylindrical coordinates, but if you think about this long enough, in Cartesian space, any coordinate is pretty much unique, right? So maybe we should write this down. So in Cartesian coordinates, right, all coordinates are unique, right? But in cylindrical, right, slash polar that we were talking about, and spherical, right, that's actually not so, right? In the sense that depending, since theta and phi are angles, right, any 2 pi multiple of those will get you to the exact same location. So a lot of times, to make it a little bit more close to unique, what we'll end up doing here is putting restrictions on valid or proper solutions of r, theta, and phi. So usually to constrain this, we were only going to consider r greater than or equal to 0, so like positive radiuses. And then theta is typically going to be restrained to be in the domain of, say, minus pi. And actually, we should be a little bit explicit. So let's make this like not inclusive to pi inclusive, right? And then phi is going to be restrained to, let's see, say similar thing like a minus pi over 2 to pi over 2. Right? Now, this is interesting because if you think about this, spherical coordinates, this is basically how a lot of coordinates on Earth are determined, right? So radius would be the distance from the center of the Earth to wherever you are, like say on the surface. And then another name for this azimuth angle is sometimes like, it's a longitude, right? And then the phi is a latitude. Right? So this is exactly how if you look up on your GPS where you're located, right, it'll give you a longitude and a latitude. Well, the longitude is basically the number or the angle you are from the prime meridian, right, or a longitude. And then phi, which is your inclination or a polar angle, is basically the angle, how far you are from, basically from the North Pole or from the equator, however you want to think about it, right, in either direction, right? Okay, so that's great. That gets us the forward transformation. Let's go ahead and now get the inverse transformations. So in other words, I want to go ahead and say that, all right, if someone gives me an x, y, and a z, what is the equivalent spherical coordinate system, right? So what is this, right? So there's a couple ways we can do this. The most robust way to go about this is basically, let's go to Mathematica or someone and solve these 3 equations for r, theta, and phi simultaneously, right? So tell you what, let's jump over to the computer and do that real quick.
All right, so let's just go ahead and solve that system of equations. We said the first equation was, well, we said x was r cosine theta sine phi. And then the second equation was y is r sine theta sine phi. And then I think we said z was just r cosine phi. Okay, so those was our 3 equations, and I want to solve this for r, theta, and phi simultaneously. Okay, there we go, and let's go ahead and assign the solution to a variable. I'll call this temp, because when I shift enter this and try to solve this, we're going to see that actually we get 4 unique solutions. So let's take a look at each one of these in turn. So let's look at the first solution. Well, this doesn't look very reasonable. It is mathematically a solution, but this is considering negative radiuses, which we don't really want. So let's move on. We don't want the first one. Let's look at the second one. Second solution is a similar story. It has negative radiuses, so we don't want that. Let's look at the third solution. Aha! This is looking a little bit more reasonable. It says that you have a positive radius, but look at our theta and our phi. This is a little bit odd in the sense that arctangent of negative, negative. So, tell you what, let's go to the fourth solution, and this looks much more reasonable here. So you've got a radius, which is positive, and then you have, this might look complicated, but basically all it's saying is that you have theta can be a 4-quadrant inverse tangent plus 2 pi, which again makes perfectly good sense because we said theta and phi can have 2 pi multiples, and it's the exact same solution, right? So we can pretty much ignore that. The only thing we want to make sure of and denote real fast and maybe point out, again, if you watched our 4-quadrant inverse tangent video, you know that Mathematica and MATLAB decide to use inverse tangent in a slightly different fashion. If I come over here and get help on Mathematica's inverse tangent function, we notice here that it does have, whoops, let me try to highlight this. It does have the 4-quadrant version, but can I zoom in on this a little bit? I don't know if this is going to work. There we go. But for whatever reason, they expect the x component to be the first input argument and the y component to be the second input argument. So again, this is arctangent or inverse tangent or atan2, however you want to think about it. But this first argument is the x component, and this second one is the y component. So when we go back over to the board and write this up, we're just going to have to be cognizant of translating what Mathematica gave us into how we might want to write it on the board, where traditionally we pass in the y as the first argument and the x as the second argument. So tell you what, let's jump over to the board and summarize and write down this inverse transformation.
All right, so what we obtained here was that the inverse transformation that will basically take us from a set of Cartesian coordinates to spherical coordinates was this. Let's write this down first in Mathematica speak exactly. So Mathematica told us it was basically z squared, right? Because this was the radius, right? Radius was totally normal. And then we need the azimuth angle theta. So Mathematica said that this was arctan of x over square root x squared plus y squared, comma, let me move this bracket over to give ourselves a little bit more room, y all over square root of x squared plus y squared. Okay, and then phi was arctan of, let me see, oops, no, sorry, this one was just z. This is just z all over square root of x squared plus y squared plus z squared. And then the second input argument was going to be square root of x squared plus y squared all over square root of x squared plus y squared plus z squared. Okay? So this was the Mathematica interpretation, but remember that we needed to be a little bit careful that Mathematica, when it does inverse, the 4-quadrant inverse tangent, it wants x and y. Okay? So more traditionally, what you would see is atan2, right? Is a little bit more popular implementation of the 4-quadrant inverse tangent. So this is going to be the same. Radius is going to be the same. Right? It's going to be square root of x squared plus y squared plus z squared. Now, theta, if you wanted to do this and solve this in, say, Mathematica or some other implementation, you would go a tan 2. But now all you got to do is just flip these input arguments. So really, this is going to be y over square root of x squared plus y squared, comma, x all over square root of x squared plus y squared. Right? And similarly for phi, you can again still use a tan 2, but you just got to flip the order of the inputs. So this is now square root of x squared plus y squared all over square root of x squared plus y squared plus z squared, comma, then z all over square root of x squared plus y squared plus z squared, right? Because a tan 2, right, typically has y and then x. So again, you just got to keep it straight which one is which. Right? Okay, so again, let's go through an example just to make sure that this all works out. So tell you what, let's go ahead and erase this. Okay, and let's use the exact same example that we had earlier. So if you remember, that was, where was it? What was the numbers we were using? Just want to make sure we're all on the same page. Okay, so example, right? We said the point in the Cartesian space was going to be -3, -1, -4, okay? So it's all in this sort of the negative quadrant. Well, I guess now it's like there's more than quads. There's like 8 regions of space here, right? But this is a location of the coordinate, right? Okay, so first let's go ahead and compute what's the Cartesian, or excuse me, what is the spherical coordinate there. So where did I have that? I just want to make sure we're all on the same page here. Okay. All right. So let's do the forward transformation. So I want this same point P in the spherical coordinate system. So I'm looking for what is the radius, the azimuth angle, and the inclination angle, okay? So we said that in order to get this, well, here we go. Let's go ahead and just run it through either one of these sets. So this is going to be, the radius is just going to be square root of, again, -3 squared plus -1 squared plus -4 squared. Right? Okay, theta is going to be a tan 2 of y, which is going to be, what do we got here? This is -1 all over square root of -3 squared. Let's make this a little bit bigger again, get ourselves a little bit more room. Plus, wait, was that x? Yep, and then y, -1 squared. Right? Okay, and then comma, and then I got to give it x, so x is going to be -3 all over square root of -3 squared plus -1 squared. Yikes, there we go, okay. Let me erase all this junk. Sorry, I'm not using the whiteboard space very well. And finally, the inclination angle was a tan 2 of this whole thing, square root of x squared, so this is -3 squared plus -1 squared, all over square root of -3 squared plus -1 squared plus -4 squared. Right? Comma, and then, yeah, gosh, all right. In the interest of completeness, just since we've already gone this far, let's just write it all out so we're all on the same page. So I need this one. Z is going to be -4 all over square root of -3 squared plus -1 squared plus -4 squared. Yuck. Ugly, ugly. This is why you want to do this in a computer tool rather than just writing this on the board. But long story short, if you write all of this out here and you just crunch all these numbers, here's what you end up with. So this is now 5.1-ish, and then this is now -161.56 degrees, and the inclination angle is 141.67 degrees. Great. Okay. And again, now what we can do is let's go back and verify that the reverse transformation also worked, or the other transformation, right? So basically, if we are given this radius, azimuth angle, and inclination angle, can we still recover that value of -3, -1, -4? So again, all we're going to have to do is run that through our normal forward transformation. Right, so all we got to do here is, again, let's call this thing x, y, z, and we'll put primes on these to denote their check values. So again, in order to get that, we just need to basically do, what was this? This was, x was going to be r sine phi cosine theta, right? And then r sine phi sine theta. And then z was going to be r cosine phi. Right? Okay, so just plug in this value of r, theta, and phi into these expressions, and yes, indeed, you do come up with -3, -1, and -4. So great. This is basically, I'm going to box it up here. This is the proper transformation from Cartesian to spherical coordinates, and this is the transformation from spherical back to Cartesian coordinates. Now, the only reason I bring this up and I'm harping on this is there are some texts and some derivations where you might see people trying to look at deriving the inverse transformation. Instead of going to Mathematica and properly solving for it, they might try to just backtrack from geometry. So, for example, you might see this as a proposed transformation. Let me write it right here so we can compare. So you might see that, oh, some people say, oh yeah, to get the radius and the azimuth angle and the inclination angle, I can get this from geometry, and radius is going to be, well, I can say that's x squared plus y squared plus z squared. And yeah, I've got no problem with that. That is totally correct, right? Let me erase this to get ourselves a little bit more room. Okay. But then they're going to look at trying to get this angle from inverse cosines, right? You can see that basically we went forward using some cosine arguments, so they think, oh, we can go back and do an inverse cosine discussion, and they might write, oh yeah, this is just arc cosine of x over square root of x squared plus y squared, right? Because you can kind of, oh, I keep turning this off, right? You can basically see where this comes from, right? Because here's theta, right? So cosine of theta is what? It is going to be x over the hypotenuse, and we said this hypotenuse was this distance right here, which is basically, it's in the plane, it's x squared, or x squared plus y squared square rooted, right, is this hypotenuse. So they'll come up with this expression, right? And then they might say that, okay, I can do a similar triangle arc cosine expression for phi, right? I can say arc cosine of z all over square root of x squared plus y squared plus z squared, right? So what's the problem? The problem here is, again, remember, if you watched our video talking about the 4-quadrant inverse tangent, we also talked about, 4-quadrant inverse tangent doesn't just apply to tangent, it applies to inverse cosine, inverse sine, right? Again, these are not one-to-one functions. The typical arc cosine or arc sine is only going to return a value in 2 quadrants, not all 4 quadrants. And you are going to get hosed if you use this expression here, because you can clearly see the difference here, right? Down here, we are using proper full 4-quadrant inverse tangents for both angles. And here, you're going to get a little bit stuck here because you're only using, a 4-quadrant inverse cosine is not a very popular operation here. And if you just plug this into MATLAB or Mathematica or whatnot, this is not going to get you the right answer. In fact, I'll leave that up as an exercise to you to show that if you do this, I think what goes wrong is if you try to compute, you'll get the radius correct, right? There's no way you screw that up. The radius is correct, but if you do this and you plug it in, I think what you end up with here is, did I actually write this down? Yeah, you end up with positive 161.56 degrees, and the inclination angle comes out right. You do also get 141.67 degrees, right? So this is wrong, right? This didn't get you what you needed here, right? So this expression is not exactly correct. And there are some situations where you could potentially have issues in maybe phi as well. But long story short, do not use this arc cosine discussion here unless you are explicitly very careful about how you interpret the results from arc cosine here, right? Which quadrant are you actually in? So long story short, if I were you, I would use this much more robust set of equations for the transformation here, okay? All right, so with that, I think this is a great spot to leave it for our discussion on, just to refresh your memory, right? We started out talking about simple Cartesian coordinate systems, which we're all familiar with, and then we saw how in 2 dimensions that expanded to polar coordinates. Then if you just add a third z dimensions, that's what we call cylindrical coordinates. And then finally, we have full-on spherical coordinate systems, and all of these systems are just basically a way to describe a point P in space, just using a different way to get there, right? And we've now defined all of the transformations to go from one to the other, so you should be comfortable working in any of these coordinate systems. So if you enjoyed the video, I hope you'll consider subscribing. Surprisingly, if you just reach down and click on that button, it really does help me continue making these videos. And with that being said, I hope I will catch you at one of our future discussions. So until next time, I'll talk to you later. Bye.